So what's up guys, I'm very happy that you choose to take the thermodynamics course. I'm going to give you the overview of what we are going to be studying in this course. And as you can see, this is TD2 or 0 because it's the beginning. And be sure to check out this site here. Now, first thing first, why should you study thermodynamics, its importance, and why you need it in your curriculum? And the first thing that pops into my mind is because you need to understand it for other energy balances and how heat is exchanged and how the heat is transferred, how can you change heat into mechanical work, and that mechanical work maybe even change to electricity, like in the plant generation. We're going to see a little bit on that. Also, it's very important the refrigeration topic, which is how can we cool a system. We can then, after this course, understand the limits of energy or the limits of heat and heat transfer, and also the interaction between work and heat. What else can we see? And we will see a little bit on the microscopic overview of energy, but mainly we're going to see more into the macroscopic overview of energy. How can we use that energy? And who's this thermodynamic course for? Probably I would say it's in general for engineers. I would say it's a very important topic, how to interact with heat and work. But of course it's more into mechanical engineering, electrical engineering, even a little bit industrial engineering, chemical and process engineering. These are the top engineering that will of course take the most advantage on the course. Or if you're in computer engineering or something like that, it might even also help you to know how chip processors may be cooled and all those kind of stuff. And I'm very happy to tell you that even though we're going to see a lot of theory, the point of the course is to apply that theory, because knowing about a lot of concepts, it's okay, but if you don't know how to apply them in real life or in engineering life, I think it's not that worth to know them if you don't know how to apply them. So still, why thermodynamics? We need to know that heat and mechanical work relationship. Many energy concepts, I'm pretty sure you don't know many type of energies that we're going to be studying in this course. Also, once again, the limitations due to thermodynamical laws. We have at least 4 laws: 0, 1, 2, and 3. We need to see a lot of power generation, especially electricity, or more how to interact with heat. We can transform it into mechanical work, and mechanical work we can transform it to electrical energy. And of course refrigeration, which is a very important industry, especially in food industry and many other chemical processes that involve having low temperatures and all those kind of processes. Also, we need to understand the difference of pure substances and mixed substances and how they interact between each other. And hopefully after the course you will know the basic equipment that we use in engineering, especially in process engineering. For example, pumps, boilers, heat exchangers, condensers, all those kind of processes, even turbines, valves, many other. We're going to see a lot of equipment, and we're going to be analyzing the mass and energy balances of each of these equipments, and of course how do they work. Now about the textbook that we're going to be using and the reference and all that bibliography you can get. The good thing on thermodynamics is that we got a lot of materials, so that's not the problem actually. The problem is which one would you choose and which one makes more sense, which one is easier to get, and which one is more available. I'm going to recommend you, if you're in general engineering, mechanical engineering, or even chemical engineering, a general bibliography that I think is pretty good. Actually, it's my favorite one. And if you're studying chemical engineering, I'm going to give you a little bit more on that. So about the general engineering, I will recommend you definitely this book, which is Thermodynamics and an Engineering Approach. because actually thermodynamics is a science rather than a subject purely engineering, but it's very important in process engineering. So that's why these thermodynamics books makes an approach in engineering, and it's pretty awesome. I really recommend it. It's actually the of all the books I've read before on thermodynamics, I think it's the one that makes more sense and is easier to get and has a lot of examples and explains you pretty well each of the exercises. And this book is written by Yunus Sengel and Michael A. Bowles. I think there's a 8th edition, but I will recommend you any edition you can get. Now, if you're studying chemical engineering, probably you will get one of these 3 books. One of the most typical ones is this one. I really recommend it if you are then going to study thermodynamics in equilibrium. It's the Introduction to Chemical Engineering Thermodynamics by Smith, Van Ness, and Abbott. I think it's good. A little bit. I will rank it 4 out of 5 stars. I think eventually you're going to buy it, so buy it as soon as possible. If you're starting with this course, I will totally recommend you guys. Now, Introductory Chemical Engineering Thermodynamics, I actually haven't read it or used it that much, but what I have been in contact to, I don't like it that much because they start giving you a lot of abstract concepts and they start studying entropy, which I think is a little bit too soon for that. I will rather start analyzing first law and then I will go to the second law. But they go directly to entropy, I think in the first or second chapter. And it's okay because eventually you're going to stumble upon that, but I will not recommend it that much if you are not a chemical engineer. Actually, as a chemical engineer, I will not that recommend it. I will give it maybe 2 out of 5 stars personally, even though it's a good book, but for as it means introductory, I don't think so that much. And then you're going to see this book, which is one of the most famous book for unit operations, actually higher subjects in chemical engineering. It's from McCabe, Smith, and Harriot. It's pretty awesome, but the thermodynamic part is not that into thermodynamics that we need, so I will not recommend it. I will give it also maybe 3 out of 5 stars for thermodynamics, even though for unit operation I will definitely give it 5 out of 5. So it's up to you guys, whatever you want to. They cover almost all the topics that we're going to cover in this course, so whatever you can get in your hands, it's good. About the basic concept you need to know before, well, you've probably seen this slide before. You need to know a little bit on arithmetics, geometry, for example, how to calculate area, volumes, even perimeter. You need to know how to convert units, like centimeters to meters, kilograms to grams, etc. And most importantly, and we're going to practice a lot in this course, is changing from English units to international system units. For example, Fahrenheit to Celsius, BTU, which is British Thermal Unit, a measurement of energy, to joules, and all those kind of units that we're going to see in here. Please make sure you at least know the equivalent or you have a table behind you because it's going to help you a lot. Decimals and scientific notation, this is very important. We're going to work a lot with, for example, kilo, mega, micro even, etc. And where else? Percentage and fraction. This is important, especially for efficiencies, vapor, quality, etc. Now on chemistry physics, actually, since this is a open thermodynamic course, you don't need to know that much into chemistry and not that much into physics. I'm going to give you a small review on difference between pressure, weight, force, mass, etc. I'm going to give you an overview on the temperatures, also what's a mole, mass, weight, how to interact between them, molecular weight, mass fraction, mole fraction, etc. So actually you just need to know a little bit math and the basics on chemistry and physics. So let me give you the course structure here, guys. TD as thermodynamics, I broke it down into 8, let's say, like blocks. Block number 0 and 8, of course, are 0% because it's the introduction and the conclusion. As you can see here, the highest one will be TD3, first law of thermodynamics. I think this is one of the most important parts in the course. If you get this, you will get easily all the other subjects here. What else? Also, pure substances. This one is pretty important because if you're going to be studying about substances and thermodynamic equilibriums and mass transfer, heat transfer, etc. in further courses, you are going to use this absolutely. Like, I'm pretty sure you're going to use it, and it's very, very important. Basic concepts is the one I'm going to be showing you. All those chemistry and physical concepts. What else do we have here? TD4 second law and heat machines. We start analyzing a little bit on heat machines. We're going to see the complete course content in the next slides. What else? Production of power. This is also very important, especially for mechanical engineers or electrical engineers. Refrigeration and liquefaction. I think it's also very important, especially for those who want to learn how to cool down systems in the most efficient way. And finally, we make the conclusion. And as I told you before, guys, this is the complete content, or at least a more in-depth content. We're going to be analyzing theory and then application of that theory. So don't think that we're going to see a lot of abstract things and never apply them. No. We're going to see maybe abstract things and then we apply it as soon as possible so you get the idea and why is it important to study that. So we start with basic concepts, as I told you before: force, weight, gravity, mass, flows. I want you to get them completely, like perfectly definitions of that. I want you to be free of doubt there. Then we start with temperature, the difference between temperature and heat, and of course the scales we have there. The zero law of thermodynamics, which is actually pretty simple. The type of systems that we are going to be analyzing: open, closed, insulated, isolated, etc. Many other definitions that maybe are easy to, or at least you've been talking about that, but not that into the most technical terms. And then we continue with the relationship between work and energy. You might think they are the same, but they are not the same. They are similar, but not the same. And since we will be talking about energy, why not introduce you to one of the most typical type of energies we're going to be finding in the industry, which is kinetic energy, potential energy, internal energy, and enthalpy. This one is special case. Good. Once we get those basic concepts, we can jump to the second block, which is TD2 Pure Substances. We're going to analyze properties of the substances, how or what is a phase, how do they change between them, all the important points such as critical point or all those points, the triple point, etc. Phase diagrams, and we're going to see and analyze a lot of them: pressure, temperature, volume, and a lot of interaction. Vapor tables and refrigerants. Ideal gases. You've probably been working with these before, but we're going to give a little insight just to say that we covered that. And then we're going to analyze real gases. This one is a pretty awesome course. Actually, you might even make a course on that, but we're going to see, of course, just an overview. Then we jump to, once we know how substances work and interact between each other, we can jump to the first law. We're going to review heat and work for open and closed systems. Then we're going to see the typical processes or polytropic processes such as isobaric, isothermal, isovolumetric, adiabatic, etc. All those, we're going to analyze them. We're going to see the relationship between mass and energy conservation. Then we see the first law of thermodynamics for open and closed systems. Once we get, of course, heat, work, and some polytropic processes. And then once we get that, we're going to make a lot of exercise, and then we apply it to many typical engineering equipment such as turbine, a pump, a compressor, a condenser, boiler, heat exchanger, etc. All those equipments that we use a lot in the industry, we're going to keep them let's say we're going to apply the first law to that. Then we continue with the second law, which is TD4, the second law of thermodynamics. We're going to see what's a perpetual machine as a concept, reversible versus irreversible processes. You're going to see that eventually this is not possible to achieve in real life. The heat engine, refrigerators, and heat pumps, those are very important. But more importantly, we're going to see the Carnot cycle and the deduction or principles that we can get from there. And when we study this, we're going to eventually get into the definition of entropy, which is a very abstract concept. But the good thing is, even though you don't know what's exactly that, you just need to know that if entropy increases, then this is possible, and therefore you will be able to be calculating those changes on entropy and know if the process might or may not be achieved. And eventually you need to know also the third law, which is a pretty simple law but very, very important and powerful law. And once we know a lot of theory or theoretical concept, we can actually start applying to production plants. For example, the steam power plant, Rankine cycle, the original cycle, or including the reheat cycle, Otto cycle, which is the one with the spark ignition engine, diesel cycle, probably you know it because it is in a lot of motors or engines right now, Stirling and Ericsson cycles, a little bit overview on that, and the Brighton cycle. Good, that's about generating power, but what if you want to cool something? You are not interested in generating power, but consuming that power into refrigeration. We're going to see the refrigerator, heat pumps, the Carnot refrigerator, and the vapor compression cycle, which is the real one, because Carnot, you will see later that this is more theoretical, this is the real one. And heat pump, which is kind of similar, but it is not a refrigerator. And last but not least, we make a small conclusion on what we've seen, what do you need for the next courses, and what you should have learned. And this was the end of the overview, guys. I'm very happy that you got everything here, and by now you should know the importance of thermodynamics and why do you need to have a solid thermodynamic basis, not only for this topic but for subject or future subjects or courses. You know the course structure, so this is very important, guys, so you know why you're studying that first and that after, and how do they structure. You see this, and once you get this, then jump to here, etc. Please note that there are 8 blocks. 2 are introduction and conclusion, and 6 are theoretical blocks. And this course is theory and application on theory. And I think that's everything, guys. I'm pretty sure that you're going to make it, and thank you for joining the course. See you in the next videos. What's up, guys? It's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.